I don't really like this person's music very much. We've just gotten to the point where it's rather difficult to find pop culture references to match the lecture number. Apologies to anyone who does like Adele's music, but no apologies for this recap, which is going to be rather extensive. So last lecture we covered two major concepts. One, how to relate these Jablonski diagrams to actual data that we would collect in a lab, spectra in other words. And we also covered the theory of what happens after light is absorbed and the molecule attempts to relax back down to ground state. So let's recap all of that using this image here. So we have this molecule anthracene, and on the left we have what's known as an absorption spectrum, which we've seen numerous times throughout this unit. We'll deal with that fluorescence spectra on the right momentarily. At this point, we should be extremely comfortable with the idea that when light is absorbed, it causes an excitation or increase in energy of the molecule. We should also be comfortable with how the molecule changes upon that excitation. In other words, there's electronic excitations where an electron goes to a new orbital and the molecule changes shape, and there's the vibrational excitations where the bonds start to vibrate more energetically. Now, the lowest energy excitation possible in a molecule upon absorption of UV or visible light is a purely electronic excitation. No vibrational energy added, just moving an electron. While it is true that we could do lower energy excitations that were just vibrational in nature, we cannot accomplish that with ultraviolet or visible light. Those types of photons have too much energy. We need to use lower energy IR photons to only induce vibrational transitions. So lowest energy excitation possible from UV or visible light is going to be purely electronic. And we know that the energy of light that is absorbed to cause this excitation must be equal to the difference in energy of those two states. We can express that energy of light as a wavelength, and we can see that wavelength be absorbed in our absorption spectrum over here. So as we're shining in ultraviolet and visible light, at 380 nanometers roughly, all of a sudden we see light being absorbed. But then a little to the left, we see other light being absorbed as well, that's shorter in wavelength and thus higher in energy since those two are inversely related. And that light absorption corresponds to the next lowest energy excitation possible in the molecule, a vibronic transition in which we not only excite the electron, but also induce a vibrational excitation, or an increase in the energy of the vibration. And of course, other vibronic excitations are possible as well. The molecule could absorb this even larger amount of energy and reach this even higher energy vibrational state. And in the last lecture, I provided more of a visual demonstration of how we could differentiate between these three different excitations here. So hopefully you can still visualize that. If not, I highly recommend you go back to the previous video where I first covered this concept and really discussed what it meant was happening in the molecule. Now, there are other vibronic transitions possible, and we see that there are other shorter wavelengths of light being absorbed, but it becomes less and less probable. Those peaks are becoming smaller and smaller. The reason why is beyond the scope of this course, but suffice to say, not all lights are absorbed with equal probability. We can see that in these three peaks here. If we were to shine in all three of these wavelengths into the sample at the same time, at the same intensities, wavelength 1 is going to be absorbed more often than wavelength 0, which in turn is absorbed more often than wavelength 2. Again, it's outside of the scope of the class why some transitions are more likely than others. We just need to recognize that that's how it is. But regardless of what wavelength light is absorbed in the first place, the molecule is going to lose all of that energy eventually and relax back to ground state. How it does that is potentially interesting in analytical chemistry. So what's a given is that the first thing the molecule is going to lose is any excess vibrational energy it's gained. So if the molecule absorbed this wavelength here, it's going to have some collisions and lose this vibrational energy. If it absorbed this wavelength, it'll have a collision and lose this vibrational energy. If it absorbed this wavelength, there's no excess vibrational energy to lose. But the bottom line is, regardless of what energy or wavelength light is absorbed in the first place, the molecule will go through collisions to lose any excess vibrational energy and reach a purely electronic excited state. Now the molecule can lose that energy in a couple of manners. The most common is to convert it into vibrational energy through this process called internal conversion, then lose it all in a series of collisions, back to ground state. That is not interesting, we cannot observe that. But a rare subset of molecules, known as fluorescent molecules, can lose that excess electronic energy by emitting light. And it should make sense that emission of light will cause the molecule to relax. If absorbing light increases the energy of the molecule, emitting light will decrease the energy. Now in this context, we call that emitted light fluorescent light. To be clear, fluorescent light is not simply emitted light, it's light that's emitted after a different light was absorbed. We'll learn later that there are ways that a species can emit light that don't involve absorbing photons of light in the first place, in which case we wouldn't call that type of emission fluorescence. Fluorescence implies that an absorption of light happens first. Anyways, fluorescence will always occur from this energy level here. Again, regardless of what light is absorbed in the first place, any excess vibrational energy is lost through collisions, so fluorescence can only happen after the molecule has at least relaxed back to this state. From there, the simplest relaxation would be to just lose all of the energy in one shot, all the way back to ground state by releasing light of this energy, which is almost equal to the energy of light that causes this excitation here. In fact, the only reason it's not identical is because these energy levels do shift a little bit after the excitation happens due to geometry and solvent effects, but that's beyond the scope of this course. But that's why the energy of this light coming back out is a little bit lower in energy and longer in wavelength than this light that's going in. And we can see that in the spectra. This fluorescent peak here, it's almost identical to this absorption peak, but not quite. Now, the emission of light does not have to bring the molecule all the way back down to ground state. It could also bring it to this level here, which would represent enough energy being lost so that the electron relaxed. We're now in the S0 electronic state, but there is still some excess energy left over in the form of a vibrational excitation, which could then be lost through a collision, and then we'd reach ground state. But the bottom line is the light that's emitted would have a lower energy and thus a longer wavelength than this light here. And we see that in our spectrum as well, right? Longer wavelength light being emitted than this one here, and then in turn this peak corresponds to an even lower energy relaxation process from emission that leaves the molecule in an even higher vibrational state, but again, we just lose that energy through collisions. So that is a rather extensive recap, but again, I think it's very important that you understand this concept and how it relates to the actual data that we generate in a lab. Notice that the absorption and fluorescence spectra are near mirror images of each other. This will not always happen in real life, but it is a perfectly normal thing to see, and we'll focus on molecules that give these mirror image spectra in this class. And make sure you also note that those fluorescent wavelengths are all longer than the absorbed wavelengths. And you should be able to figure out why that is just by looking at these diagrams and understanding the processes that are occurring. If it's not clear, please ask about it in Zoom. Speaking of Zoom, here's a clicker that we'll do in the session. But for now, let's move on to discussing why fluorescence is interesting in analytical chemistry. So what is this doing here? Well, we'll get into that momentarily. First, let's see if I can make this video feed look a bit more fitting for this mood. Now, too distracting. All right, so I want to discuss two major advantages that fluorescence spectroscopy has over absorption spectroscopy. And the first one I'm going to show up front with visuals, and then we'll write some notes. So anyways, what is this thing here? Well, that's a blacklight poster, which was a big deal in the 60s, and still a big deal when I was in college. Not that I was from the 60s, but we still had blacklight posters in many dorm rooms back then. The idea was that while they already had a distinct appearance about them, when we put them under a blacklight, they emit this interesting glow. What's happening is that this light here is shining in violet and invisible ultraviolet light into this poster, which is made with fluorescent dyes that absorb that energy and then emit distinct wavelengths back out. Now, from what I understand, these types of posters aren't very prevalent in colleges anymore, but something that you very well may be familiar with is laser tag, where the same type of concept exists. We have these black lights above, and we have these walls and columns coated with fluorescent dyes that are absorbing that ultraviolet radiation and then emitting these longer wavelength green and orange and red wavelengths back out. Notice the floor is not fluorescent at all, so it's just weakly reflecting back this violet color, just like we would under these lights. And so when a molecule is fluorescent, it emits a very distinct light, and we can exploit that for analytical purposes. Here's a great example of that. And this example is from the fluorescence lab in Chem 2124, so some of you should definitely recognize this. If you haven't done the experiment, don't worry about it. I'm going to cover the important points now. In this experiment, what we do is we take a liquid multivitamin supplement and try to analyze the content of riboflavin, vitamin B2. Now, riboflavin by itself absorbs light roughly around these wavelengths, which is rather simple and straightforward to analyze. But unfortunately, in the multivitamin, riboflavin is not by itself. It is mixed in with many other vitamins, all of which absorb different wavelengths of ultraviolet and visible radiation. And all of these different absorption peaks just combine to give this convoluted mess where it's impossible to actually see the riboflavin signal itself amongst everything else. And so we can't actually really analyze this spectrum. It's too convoluted. But riboflavin, unlike every other vitamin in that supplement, is fluorescent. It gives this neat glow that we can easily observe if we have a concentrated enough solution and we put it under blacklight. And we exploit this in analytical chemistry because while all those vitamins might absorb lights, only the riboflavin will subsequently emit light, and thus its fluorescent spectrum is far simpler to analyze than the absorption spectrum. It's just a simple peak, which we can easily analyze. Note that the wavelengths coming back out are longer than the wavelengths that were absorbed in the first place. That agrees with our theory from before. Also note that this wavelength here, 525 nanometers roughly, corresponds to green light in the electromagnetic spectrum in agreement with what we would see visually under a blacklight. And so let's make some notes. Fluorescence, spectroscopy, advantages. Fluorescence, spectroscopy, advantages. There are two major advantages, one of which we just covered. Not all species do it. Not all species do it. This gives a unique signal. Unique signal. It is rather unlikely that in a mixture you're going to have two different fluorescent chemicals that are also emitting almost the same light as each other and creating a convoluted picture like what we saw before in the absorption spectrum of that multivitamin. The other major advantage, it's more sensitive than an absorbance experiment. More sensitive than absorbance, which I'll just abbreviate, ABS, experiment. By more sensitive, what I mean is we can study lower concentrations. Study lower concentrations. We'll cover how that works in the next video.